Okay, so here's the tutorial to get the torsional base shear distribution of earthquake in a given framing plan. So our example here is where is an earthquake base shear acting at the Z direction or north to south. Okay, so I have here two PDF open. So pakita ko lang how the torsional shear distribution is calculated at fourth floor, okay, on that frame. So you will observe we have 6 frames here, okay, 1, 2, 3, 4, 5, 6, which is consistent with this one, 1, 2, 3, 4, 5, 6. Okay, the calculated base shear at fourth floor is 118.14 kilonewton. Therefore, our torsional moment is 118.14 times the eccentricity, 1.14 meters. 1.14 meters is derived from the formula 0.05 times 22.7 meters. 0.05, that's the provision of the code of 5% accidental eccentricity. 22.7 is the overall dimension the of our frame. 22.7, which is this one. Actually, this should be 22.7. Okay, 22.7. Because we have 9 here, plus 9 is 18, plus 4.7, that is 22.7. Okay, so back here, so that's the eccentricity multiplied to the base shear at the fourth floor. So we have 134.09 kilonewton meter. The idea is this 134.09 kilonewton meter will be resisted by the frames 1 to 6. Okay, so I discussed already how K was derived. So this is an arbitrary number because because the column sizes are equal. Okay, so it will be a different story if the column sizes are different from each other. How about the D? Okay, so remember our longer dimension is 22.7. Okay, so half of that is 11.35, which is I use an Excel here. Okay, this one 22.7. So half of that is this one 11.35. So mid span. Okay, or say the middle or the center of mass. Say you could say that is the center of mass location. Okay, assuming symmetric, the distribution of the weight are symmetrics. Okay, 22.7, 11.35. Then this one is 1.135. If you will observe, that's the 5% or 0.05. Okay, so I'll input 5% of the dimension. Okay, okay. Then this 4.5 is the distance from 1 to 2. This one is from 2 to 3. This one is 3 to 4. This one is 4 to 5. This one is 5 to 6. Okay. So these are the dimensions. 4.5. Okay. 22.7, the overall dimension. Okay. So the distance from the new center to frame 1 is 10.215. Okay. Hindi, okay lang sir. Para sa kanila din naman to. So, 10.215 is obtained by, okay, 11.35 minus the eccentricity. Okay. So, that is 10.215. Then, frame 2 the distance of frame 2 to, so we can assume that the direct shear is acting at the center of mass, which is around here. So we are getting the distance from of frame 2 to this new centroid. Okay. So that is needs 22.7 over 2 minus this 4.5. Okay. So that's it. So 5.715. So then add the eccentricity. Then the distance of frame 3 is 1.215. So this is the formula. Okay. So you will see center of mass location minus 4.5 distance, another 4.5, then add and then another 1.135 due to the eccentricity. Okay, so that's it. So you will observe these are consistent with the calculations here. Yeah. Okay. Okay. So kd squared is obtained by just multiplying this k and this d. K times d squared is this one. Then sum them up. You have summation of kd squared. Okay, then you have another table, another column, kd squared over summation kd squared. This one divided by this one is this one. Okay. Then mt over d is simply mt over the corresponding d. So ito. Therefore, so this is 134.09 over negative 10.21. Okay. Then the formula of fj double prime y is simply multiply this to this. Okay, so 13.13 times this one is negative 3.74. Okay. Again, our fj prime y is the base shear. Okay, the direct shear. So these are constant. Because the assumption is each frame will carry 19.69. Simply divide the base shear by 6 because there are 6 frames resisting the base shear. Then finally, the fjy is simply the sum of fj double prime y plus fjy. So 15.95. So once you have that, and then you will apply that to your frame, which is here. Oops. So just this, then up and then solve, then get the shear and moment by factor method. Okay, so that's